Good morning, everybody, and welcome to our 10th episode of Loops. Today, we're going to speak about bio-based resins and coatings. My name is Maximilian. I'm the host of today, and we're speaking with two amazing Horizon 2020 projects, TOMAPAINT and LIGNICOAT. LIGNICOAT is represented by Dr. Palazzi and Dr. Wróblewska, whereas TOMAPAINT is represented by Dr. Angela Montanari and Dr. Barberi. Viviana and Ola, do you like to tell us something about you?
Yes, so
Yes, absolutely.
no, go ahead, Ola, please.
Yes. So my name is Ola. You did good on the name, by the way. I'm material scientist working with LIGNICOAT. I'm representing organization VITO, which is Flemish Institute for Technological Research, and I'm going to tell you about polymeric coatings that are the target of our project, more specifically bio-based coatings. I'm material scientist, and I'm going to talk about material part of the project.
Hi, good morning. I'm Viviana Polizzi. I work for Vito in projects that aim to valorize lignin, and my background is analytical chemistry, and I work in the LIGNICOAT project to indeed, you will see later, we will introduce it soon.
And what about you, Angela and Tommaso?
Yes, good morning, everyone. I'm Tommaso. I'm one of the co-founder of TOMAPAINT, and in TOMAPAINT, I deal with the operative actions of the company. My background is I'm a geographer, and I have a PhD in environmental engineering.
Good morning. I'm Angela Montanari. I'm CEO and scientific coordinator of TOMAPAINT. I'm a chemist, and I have a long experience in the research about material for food packaging.
Okay. Before we start, I would like to address our audience that you can ask questions at any time in the comments, and we will pick them up later when we get to the Q&A sessions. So moving on, LIGNICOAT, do you like to present your project and tell us more about it?
Yes, I will start with presenting. So I will share my screen now. You should be able to see.
Yeah, we do.
Okay, so good morning, ladies and gentlemen. I'm Viviana Polizzi, a researcher working at Vito, and today my colleague Ola Wróblewska and myself have the pleasure to give you an introduction to the LIGNICOAT project and to give you a flavor of the science behind LIGNICOAT. Sorry, I have troubles. Yeah. After giving you introduction to the project and to the expertise present at Vito, we will give you an overview of the two tasks in which Vito is involved in LIGNICOAT, namely lignin depolymerization and lignin epoxies. Let's start with giving you the full name of the project. This is sustainable coatings based on lignin resins and bioadditives with improved fire, corrosion, and biological resistance. The main objective of the project is to demonstrate technical and economical feasibility of the use of lignin as raw material to produce bioresins for different applications in the field of functional coatings. A second objective is to increase the bio-based content. The challenge is to substitute fossil-based resins, maintaining at least the same performance. To do this, new bio-based value chains are necessary. LIGNICOAT covers the whole value chain for three coatings, type of coatings, and which are formulated with a bio-based approach and which contribute to make the transition to a low-carbon circular economy. How do we cover the full value chain? We start from the biosource, which is lignin. And we modify the lignin in the 3 research lines to obtain lignin intermediates, which will be used to synthesize resins. These resins, in turn, will be formulated into coatings. So we develop biopolyurethane coatings, alkyd coatings, and epoxy coatings. Moreover, in the project, bioadditives are developed and introduced in the resins to give extra features to the final product, such as fire protection, anti-corrosion, and antimicrobial properties. VITO stands for Flemish Institute for Technological Research. VITO is an independent research organization in the area of clean tech and sustainable development. Our mission is accelerate the transition to a sustainable world. You can see here in the slide some numbers. VITO has almost 1,000 employees. We have a strong collaboration with other universities of research centers as well as industrial partners. And for this reason, we host several international employees as well as several postdocs and doctoral students. VITO is made by 5 units, and our group is working in the sustainable chemistry. So we work in new value chains from renewable and circular resources such as biomass, like lignin, CO2, and plastic recycling. Also, we work in process transformation, for example, new chemical synthesis. Vito is also co-founder of the shared research center BioHorizon, which has the aim to be the profitable way to bioaromatics. We valorize biomass residues and recycled streams by applying different chemistry to convert biomass to bioaromatics and obtain highly functional renewable building blocks. BioHorizon is made by 3 horizons: sugar to bioaromatics, lignin to bioaromatics, and conversion of biomass to bioaromatics. And Vito is responsible of the horizon that converts lignin to specialty chemicals of a high end value via catalytic depolymerization. So why lignin and what is lignin? Lignin is the second most abundant renewable carbon source on Earth. In fact, it constitutes 15 to 35% of lignocellulosic biomass and is characterized by a aromatic and oxygenated structure. How do we go from lignin to bioaromatics? We apply different steps. The first step is dissolution. Dissolution means that the original lignin sample is dissolved in a solvent. And Vito, as our group, has an extensive expertise in studying how the lignin structure is affecting solubility. And via the aid of software, we are also able to match the best solvent for a specific sample. The second step will be depolymerization, which means that the lignin structure is cut in different points, so different bonds are cut to obtain lignin fractions or depolymerized lignin, which range from monomeric to oligomeric structure. These mixtures can be used as such or after chemical modification or after further fractionation to be used in synthesis of biopolymers. So all the expertise concerning these steps is present in our group. Now, from previous studies, we know that when you start from polymeric lignin and you try to integrate this in a material, often the quality of the material will be quite poor. But we also know that via depolymerization, we in fact lower the molecular weight and the dispersity of the lignin bio-oils or depolymerized lignin, which will be more reactive, homogeneous, and soluble, and so they are the most suitable for polymer development. In fact, you see here in the slide below that by applying the polymerization and using these fractions, we are able to increase solubility, like in different solvents. Like you can see that the residue in each tube is much less, or it's almost gone from compared to the original lignin. And we are able to obtain, here we give the example of a fine material, so a polyurethane. I would also like to stress that Vito is very strong in networking and in analytics. So that means that we have several collaborations with different lignin suppliers, and we also cover the full value chain. So we also have several collaboration with end users, so with industrial partners that would like to test the fractions directly in materials and in applications. This made possible that we could build a very strong database with analytical characteristics of over 100 or almost 130 polymeric lignins, and we also have a second database which study characteristics of the obtained fractions, and this allow us to study the structure, the relationship between the structure of the original lignin and the one of the obtained fractions with the properties of the final material. Now I will give you more detailed of how lignin depolymerization is used in LIGNICOAT. LIGNICOAT project will pave the way for the optimization of lignin depolymerization conditions related to their application in epoxy resins and coatings, as well as in polyester and arcade resins. One of the main objects of the task was to study and to select the best process conditions for the polymerization. So here I give, you can see examples of the variables of the process conditions that we studied, for example, the catalyst type, the solvent, and so on. We are also taking into consideration which variables of the lignin type can influence the quality of the depolymerized lignin. So concerning these variables, you can think about the two lignin types we receive from the two lignin providers, Stora Enso and CMB, that supply lignin in the project, but also we are in contact with the lignin supplier to be able to receive lignins that have been extracted from feedstock harvested in different time in the year, in different years, and also isolated from the feedstock via different process conditions. So we are able to study the variability of the initial lignin structure and how it influenced the quality of the polymerized sample. Another very important task is upscaling, and I will tell you more in a while. In this slide, I give you an example of how we can optimize the process conditions. So you see on the right hand side the feed, so the original lignin that is characterized by a high molecular weight and a very low or zero monomer content. By applying depolymerization, we obtain, by using different catalysts, so each point is a sample, the polymerized lignin that has been obtained by different catalysts, we are able to lower the molecular weight consistently and to also make that some certain amount of monomers is produced. Because of our analytical capabilities, we are able to characterize these samples and, for example, by GCFID. Here I give you just a short list, but we identify many more compounds, and we know that for this specific application for epoxy resins, the bifunctional compounds such as propanol guaiacol, which is characterized by two hydroxyl groups, so it's a bifunctional compound, is preferred for epoxy application. And so that allowed us to select this catalyst because it has a higher content of this compound, but also as one of the highest depolymerization yields. And we select this catalyst for the following step. So here you see our trajectory of upscaling. The process conditions are studied in batch systems, and these allow an output of 2 to 5 grams per day. Vito has been working very hard on the upscaling. We also received some funding from European project for this, and also our own investment for first of all upscaling to a continuous system in lab scale, which has an output of 4 to 20 grams per hour, and later this year the pilot, which is already almost finished, let's say, this pilot plant will be finally operational and is will allow a continuous depolymerization of material to obtain bioaromatics with an output of 1 to 4 kilo per hour, and with the final aim to enable commercialization of bioaromatics and to provide samples to industry in enough quantities to be tested. So I will give now the floor to my colleague Ola.
Thank you, Viviana. So I'm going to tell you about another work package, another task in LIGNICOAT, and this is lignin epoxies. Shortly, I'm going to tell you what are we doing, why are we doing it, and how are we doing it. So Viviana already introduced lignin and where it comes from. Typically, it comes from industrial waste, and it is built of this aromatic and phenolic building blocks. But what she didn't tell you is that these aromatic and phenolic building blocks are crucial in the polymer industry. You can find them as main components of materials for composites for windmill blades, cars, pipes, bicycles, protective coatings and paints, and also, for example, in glasses, sunglasses or normal glasses as lenses. And for polymer development, we typically use different phenols and bisphenols, and these materials are typically very fossil-based. There is a high global demand for them, and they are quite expensive, and they are toxic. But in LIGNICOAT, we mostly address a fossil-based character of these materials in order to minimize plastic impact, negative impact on environment. And typical epoxy resins are synthesized from bisphenol A by reaction which is called epoxidation. And you can find these epoxy resins in such an application like DIY movies on the internet. It's very often used, but also in engineering plastic or super tough protective coatings. And in LIGNICOAT, we want to replace bisphenol A with lignin, and more specifically with depolymerized lignin. However, how it is always with innovations, there are certain challenges that we need to overcome in order to do so, to reach our targets. And this is incompatibility of lignin, a variation in lignin structure, and also production capacity. And now I'm going to walk you through these challenges and explain a little bit how we tackle them in this project. So first of all, incompatibility. So Viviana already told you that high molecular weight fraction of lignin is very often not soluble, not compatible with other components of the material. Our unique approach is that we combine, actually in one building, our depolymerization team, our material scientists. And we are having a continuous feedback loop between two teams. So how does it work? For example, our depolymerization team is depolymerized lignin and gives us this fraction. We are testing them and giving them feedback what worked and what didn't work. Then they can tailor-made and optimize the polymerization in such a way that we can create top quality materials according to industrial standard, and we can have deep dive into material structure property relationship in the process. But also, when you depolymerize lignin, you get the materials that have variety of structures. So, for example, you can have in the polymerized fraction a lot of monofunctional compounds that have only one functional group on the molecule, so they have functionality below 2. The presence of this type of compounds can lead to defects or plasticizing effect of the material. By our means of identification of this compound via gas chromatography, we can actually tailor this distribution by application of new purification protocols and investigating the molar mass and molar mass distribution via gel permeation chromatography. Gel permeation chromatography measures molecular mass of material, and I would like to give here an example. So, for example, below you can see typical chromatogram that we obtain, and epoxidized polymeric lignin is not on this chromatogram because it is just simply not possible to dissolve and measure. When you take crude bio-oil, crude fraction from our depolymerization and you epoxidize it, you can see that you have a lot of red peaks in the lower parts of molecular weight distribution, which means that you have monomers, monofunctional compounds. However, after application of our protocol, our distribution shifts a little bit, eliminating low molecular weight compounds, but it's not big enough to make it not soluble. The last aspect is also production capacity that we have to take into consideration, because in order to meet the market demand, for aromatics, you need some certain production volume. And we tackle it, of course, by installing our own pilot plant where we can increase the production and we can actually deliver. But we are also dependent on feedstock providers, and we are also dependent on our application side, our end users. So, long story short, we need partners. We cannot go reach this target yourself, and we participate in multiple collaborations like BioHorizon or with Scion or with Westlake, who are also participating in this work package. And we have experience in building new value chains and sustainable supply chains. And now, as we speak today, this is actually our year one for Vito, and we're now working mostly on depolymerization and epoxidation. However, we hope that after the project, we will have fully developed lignin epoxy materials for coatings application, and our continuous depolymerization facility will allow us to deliver more and more material to our partners. And we have to also remember that LIGNICOAT is certainly not only Vito and not only epoxy resins. We work with multiple partners crossing borders. It's an international consortium with a lot of interesting research line and interesting objectives. So please stay tuned. You can follow LIGNICOAT webpage in order to access more information, or just scan the QR code on the slide, and you can get much more fuller information. And also, I would like to say that we as Vito, as our team, we are a sustainable polymer technologies team, and also this is not our only research line. So if you are interested in our activities in other projects, please also you can visit our webpage at spotvito.be. Thank you very much, and we are open to questions.
Thank you for your presentation. The questions I would like to address in the Q&A session, and we already have a question from our audience. And I would like to point out that our audience can at any time comment the question in the chat, and we will pick it up later. But moving on, we have another interesting project, which is TOMAPAINT. So Angela and Tommaso, would you like to start?
Yeah, thank you. I'm gonna share my screen. Okay, now you should see my screen.
Yeah, we do.
All right, so good morning everyone again, and again my name is Tommaso Barbieri. I'm one of the co-founder of TOMAPAINT. TOMAPAINT is a green startup that was founded in March 2019 in Parma, in the north of Italy, and TOMAPAINT is also correspond to the name of the EIC Accelerator project that is a one partner project. Can you see my screen, the presentation?
No.
No?
It's
just let me do again.
okay. Yeah, no worries.
Maybe now?
Yeah, maybe the problem was that I had Wi-Fi problems all of a sudden. So maybe because I'm hosting the episode, that was the issue, but I'm not sure. So, but
No,
moving on.
Yeah, I think I just shared the browser and not the whole screen.
Oh, okay.
And yeah, so we developed a natural bioresin obtained from industrial tomato processing byproducts. This new bioresin has numerous high-value applications. The first application that we are focusing on is its use for the production of biolacquers for coating food metal cans. as a natural substitute for conventional petrochemical-based lacquers. We are in line with the principles of the circular economy because essentially our business takes an agro-food industry waste and turns it into a high value material. Tomato byproducts production is about 300,000 tons per year in Europe and 70,000 tons per year in Emilia-Romagna, that is our region. These numbers mean that we have enough and cheap material for an industrial project. We can also say that we can say that our bioresin is a locally sourced bioresin. The starting substance for our process is cutin. That is a component of the cuticle of tomato peels. And I have an echo, sorry.
Yeah, Viviana, could you mute yourself, please? I think it's coming from you, but I'm not sure. Maybe it's from Tommaso self. So,
And
thank you. Is it better now?
Yeah, it's better. Thank you.
Okay.
The composition of tomato skins cutin has just been extensively studied in relation to the plant's botany. The tomato cutin is a polyester biopolymer interesterificated with potential to replace petroleum for the synthesis of polymer. The 1016 dihydroxyhexadecanoic acid is the principal unit of tomato cutin as reported in literature. The process of cutin extraction has been patented at national and European level, and also a new patent has been registered, and it's under evaluation. The procedure of extraction of cutin from tomato peels consists in a separation by flotation of the peels from the seeds, and it is followed by a thermal treatment of the skins in alkaline solutions. Then the cutin is precipitated by acidification and separated by centrifugation. The cutin extracted is a kind of solid paste that has a brown color. And since we do not use organic solvent, we can say that our process is a green process. The goal of the EAC process was the scale up from the pilot plant to an industrial plant, so the realization of an industrial plant. And here in this slide, you can see some pictures of our new industrial plant that we realized thanks to the funds. The plant has potential production capacity of about 500 tons per year. That correspond to 200 tons, as you can see here, working on one shift. And in this moment, we are in a setup phase, and we are making some changes to optimize the initial layout. The process is a continuous process, and the plant complies with the requirements of the Industry 4.0. And in collaboration with IRIS, that is a Spanish engineering company, we realized a continuous monitoring system in order to check in line the quality of the product. In particular, we analyze using Visum inline units, mainly three parameters: the suspended solid, the sugar content, and the pH. And of course, these parameters have an important influence on the the quality of the coating of our product. And in order to evaluate the climate impact of TOMAPAINT resin, the TOMAPAINT resin production, we evaluated the LCA analysis performed with CIMA Pro software. The analysis has been executed using the database EcoInvent3. And as you can see, the advantage of coating resin process of production compared with a resin type competitor, such as the epoxy resin. The analysis of impact was evaluated for each of three categories of damage: the effect on human health, on climate change, and on depletion of resources. And it is clear that, especially for on the last type of impact, the depletion of resources, the TOMAPAINT resin get a great advantage because it uses a byproduct of other process and not oil derivatives. And also the analysis of greenhouse effect shows a significant reduction of carbon dioxide production. That is 4.8 kilos less of carbon dioxide per kilo of coating produced in comparison with 1 kilo of epoxy resin produced. As I said before, the first application we focused on is the one related to the food metal cans. Currently, food metal cans are internally coated by oil-based lacquers in order to protect the food, and this implies that the risk of food contamination with dangerous substances increases, as well as the consumption of fossil resources. The solution that we offer is to replace the synthetic resins with our natural bioresin in order to formulate lacquers more sustainable and safer for the consumers. And we are working in order to create a new value chain that fits with the circular economy approach, enhancing and of course reducing wastes. Coating-based lacquer for the application to food metal packaging are under development. The biolacquer will substitute standard oil-based lacquer with comparable performances. As the lacquer will be used in contact with food, chemical analysis of pesticides and heavy metal has been performed, and no pesticides and heavy metal were found. And moreover, the bioresin doesn't contain BPA and doesn't modify the sensory properties of the food. And also, we have been verified the compliance with the European legislation for food contact. Some formulations were developed and applied on tin plate sheets. Main properties were tested, and chemical and mechanical resistance, adhesion, and porosity. And the results of the analysis carry out good performances compared to the reference standard. The University of Ferrara developed two formulations of coating-based lacquer to coat aluminum alloy. The first formulation was cured at room temperature, the second one at high temperature, and the results of the study highlighted that the application of coating base lacquer to coat AA2070T4 aluminum alloy sheets at a grammage of 6.5 grams per square meter gave a high corrosion resistance after 15 days of exposure at the acidic pH at 30 degrees. And the same good results have been obtained for a coating-based coating with similar grammage applied on AA6063 aluminum alloy sheet. And so both these tests demonstrate that cutin-based lacquer give a high level of protection of metallic substrates. In relation to the market opportunity, the global resin market amount to 2 billion euros, with our national, that is the Italian market, occupying the 20% of European market, that is about 90 million euros. And we are focusing on our batch head segment on metal packaging for organic products and for the green label of large retailers, which has a value of about 10 million euros. The target market data in other cutin application sectors are 8 billion euros for the wood sector, 400 billion euros for the cosmetic, and 45 billion euros for the paper packaging coating sector. As I said before, in our market entry application, the bioresin will be the main component of lacquers for food metal cans, and our application roadmap extends to metal cans for non-food products, as well as to others metallics substrates for industrial use. And we are also focused on additional applications, such as coating for paper, bioplastics, and cosmetics, and also in collaboration with an Italian company, we are evaluating the application of the bioresin on fabrics, and also with a foreign company, its application in the gardening sector. Well, in order to increase the know-how and the knowledge of new applications, we started collaborations with universities. The collaboration with the University of Ferrara is focused on the chemical and formulations aspects, while the collaboration with the University of Parma is related to the engineering aspects, and the collaboration with the University of Salzburg is aimed at a particular application for wooden floors. This is the last picture of our team. This is, and thanks to the funds, the EIC Accelerator funds, in addition to the 4 co-founders, we hired we had the opportunity to hire some employees, creating jobs in the bioeconomy sector. Thank you. Me and Angela, we will be happy to answer to the question. Thank you very much.
Thank you for your presentation. I would like to ask if there are any further questions from our audience. And yeah, then we're going to have the Q&A session. So do you have any questions for each other? Or yeah?
Yes, actually, Tommaso, thank you very much for this presentation. It was really great. You guys are doing a great job. And I have tons of questions, actually. But I would like to start because, I'm a chemist. And so you told that you have a difunctional acid, which is mostly the main ingredient of your tomato plants, waste from tomato plants. Could you tell me what type of resins actually you're aiming at? So chemically speaking, are there epoxy, polyurethane, or alkyd, polyester resin?
Thanks for your question. In fact, the resin that we obtain is a polyester resin. And during our extraction process, we partially depolymerize the natural biopolymer bioresin, cutin, and after the extraction, we repolymerize the cutin in order to use cutin as a main component of a biolacquer.
Okay, and can you also use this main ingredient? Did you also explore other applications with other resins, transformations?
No, the project was focused on the scale up of the extraction process from pilot scale to industrial scale. So the objective of our project was to realize an industrial plant with a high capacity of concerning cutin obtained extracted from tomato paste, but it is possible to modify the process, partially modify, and obtain cutin from other vegetables.
Okay, that's really interesting. Thank you.
I have a question for you because it's very interesting. Just a comment. It's very interesting the possibility to obtain from lignin a substitute of BPA. In fact, also our project was developed at the beginning in order to substitute BPA in the lacquer for food metal packaging.
Yes, yes, I agree. That's very important.
Okay, we have a question from our audience to where is the linen sourced from? It is feasible to source it from bio-waste, like urban waste from parks and gardens, or waste wood from woodworking companies.
I will pick up this question. So, so in the project, we have 3 companies that belong to the advisory board, and 2 of these companies are lignin producers. So, the lignin is, we have 2 types of lignin. One is a kraft lignin. So, kraft lignin, for who is not familiar with the topic, is you can say it's a side product of the paper industry, and it's already available at commercial scale. And the second lignin is what's called organosolv lignin. So it's a process that starts from wheat straw. So it aims to valorize a waste in Europe. And the lignin is extracted from wheat straw via this organosolv process, which actually, compared to the kraft, gives a lignin of higher purity. So in this specific project, in fact, we focus on these 2 types of lignins, but we have several other collaborations, and in that case, lignins come from several other types of processes. And some of these, they also try to valorize waste. Okay. I hope I answered the question.
Yeah, I hope so as well. I have a question for TOMAPAINT, and like you mentioned, your product is BPA free, and I know that the problem for traditional coated canes is that, for instance, cyclo-D-Butch CDB is leaking into the product over time. Is there a similar problem with your coating, that something in your resin is leaking or getting into the end product over time? Or have you solved this problem?
In our lacquer resin and the lacquer developed with our resin, there isn't BPA or other monomer or oligomer that can migrate in the food, but all the lacquer comply with all the European and regulation for food contact material. So even if some substances can migrate in the food, but it must migrate under the level fixed in the legislation.
Okay, thank you. That's pretty good. Yeah, I have a follow-up question, and it's regarding your production sites. We know that, or it's known that China, followed by India, is the biggest producer of tomatoes. So are you planning to set up sites there, or is there a way to ship the tomatoes or the ingredients you need, the raw material, to your construction site without losing it um, to degradation or something?
Yes, at the moment, the amount of tomato byproducts is enough for the amount of cutin that we have to produce. But of course, in our business plan, we plan to replicate our plant. We were thinking also also before to go abroad, I mean, out of Europe, we were thinking also to the south of Italy or countries in Europe such as Spain or Greece. And then, yes, we are conscious that also China or Turkey are places where there are a huge amount of tomato byproducts that we can use. And another opportunity for us is also to not just to replicate the plant, but to give the licenses to let other companies replicate the plant in their own country.
Okay, that's good. LIGNICOAT, I have a question regarding your delivery 3.4, the new enzymes against VOCs. So you're still using VOCs in your products, but you're aiming to make them safer, right?
About the VOCs, I Ola, correct me eventually if I'm wrong, but I think that the point is that the final material is characterized usually from emissions of volatile organic compounds, and this the legislation as well as in the coating field has been pushing to minimize this volatile emission, and the introduction of enzymes in the resins will make it possible to degrade these volatiles, these compounds, before they actually go into the atmosphere, so before they become volatile. So that's more the topic.
Okay, thank you. And compared to fossil fuel prices nowadays, would you say that lignin-based products are becoming more feasible and stable in price compared to traditional resins or products?
Well, we are getting there, certainly. Yes, there's progress made here. And in terms of, what is now the most important thing that we need to do is lignin availability, that we are working. We are building plant, yes, and we hope that it's going to be more and more in future. It is already available commercially. But the other thing is, another challenge is to equal the properties of lignin-based materials with traditional materials. And this is also the progress of different research institutes, and also Vito is being made every day, and our resins indeed actually now can reach industrial standards. So they become attractively priced, not only necessary from environmental point of view, but also attractive in terms of properties that we can obtain.
That's good. So I have a few more general questions. We're speaking about the environmental impact a lot. So how environmental friendly and recyclable are your products? I mean, it's just because something is made out of tomatoes doesn't, in a chemical way, doesn't need to be environmental friendly in the end. So that's the question.
Is it for LIGNICOAT or TOMAPAINT?
For both of you.
For both. So since I'm already talking about it, let me say. So so in this project, we're using bio-based replacement for fossil-based materials, and we are not tackling a problem of recyclability. So in this matter, our products do not possess improved recyclability. So we are kind of approaching way from a beginning of life perspective. Yes. However, by optimization, it's still very important, yes, in terms of using finite resources from environmental point of view or from even political point of view recently, yes. So the impact, we mostly impacting beginning of life.
Okay.
Well, related to the question, to the price question, since we just realized the industrial plant, we have an idea of the price, of the cost of our resin, that based on the theoretical costs of productions. Of course, the price is higher than the standard resin, but due to the increment of the costs and of the prices during due to the pandemic situation, the difference now is there is less difference between our price and the standard resin price. And I let.
And about concerning the environmental impact, the main advantage of TOMAPAINT of our resin is the valorization, the use of byproduct, tomato byproduct that are produced in large amount in the tomato industry, and that actually are used for animal feed or dispersed in landfill. So this is the main advantage. And when the bioresin is used as for the production of lacquer for food metal packaging, it is not biodegradable for chemical reason, but when there is the possibility to produce a bioplastic film cutin base, in this case it is biodegradable.
Okay. So how easy to handle are your products compared to traditional products? I mean, in LIGNICOAT, in the presentation, we've seen or they mentioned the DIY side as well. So is it for the DIY community easy to handle enough, or just for industrial use?
It should be. At the end, it should be. So how we're doing it, so lignin, what we produce, it's typically solid. However, in the process, later in the project, the plan is to synthesize liquid epoxy resin. And then, as a final product, it will be as easy to handle as, for example, this one that you can make a table of or some other product. So for the time being, we still have powder, but indeed the aim is to solubilize and to homogenize it with liquid components.
The cutin base lacquer was formulated in order to not modify the standard line of application. So the lacquer can be applied, has been formulated for the application of standard line, industrial line, and we have already applied on industrial line the lacquer. For other application, is necessary to solubilize the cutin bioresin in alcohol solvent or in water.
Okay. So thank you for answering all my questions. If there's another question we could address, well, we could happily do that. If not, then I would say we're at the end of today's episode. Thank you. It was a lovely discussion, and I learned a lot. It's fairly interesting what you're doing. And do you have something to add?
Just maybe thank you for inviting us. It was
Yes,
great.
indeed. Thank you for the invitation.
Thank you for the invitation.
Thank you very much. Thank you.
Thank you. Then have a nice day and see you in the next episode. Bye.
Bye bye.
Bye.